Yesterday we reintroduced the idea of diffraction. We introduced it for the first time last year in Physics 20, but we reintroduced it yesterday. We redefined it again as the spreading out of a wave around a barrier or through an opening. Now, that's in contrast to refraction, which is the bending of a wave. Waves bend. Light bends when it goes from one medium to another because it changes speed, changes direction as a result of that. But when it goes from around a barrier or when it goes through an opening, it also bends or spreads out, not bends, it also spreads out around that barrier or around that opening. We extended that yesterday to look at diffraction taking place in two places. In other words, two openings. We still get a diffraction pattern through both of those openings. The diffraction pattern will look something like this, right? The light or the wave, whatever kind of wave it is, spreads out. But through the other one, it's going to look the same. Then we end up getting a whole bunch of different lines matching up with lines and crisscrossing lines and so on. We call that interference. When one wave hits another wave, we get a pattern of interference. Now, there's two types of interference that we can see. What are they? Constructive and destructive interference. When do we get constructive interference? Sorry? Yeah, if two crests hit each other, that's a bigger crest, that's constructive interference. If two troughs hit each other, that's a bigger trough, that's still constructive interference. When do we get destructive interference? Yeah, when a crest meets a trough. Now, we saw yesterday, we're not going to go through this entire derivation of this pattern again, but we saw yesterday this basic pattern that forms when you have this diffraction taking place from two openings nearby each other. We get what amounts to a line of constructive interference, and then we get a line of destructive interference on both sides. And then we get a line of constructive interference. And then we get a line of destructive interference. And so on, and so on, and so on. Now, if these are water waves, we can physically see these lines of constructive and destructive interference, these antinodal lines and these nodal lines. If we look at them from above, we can see them. But if it's light, we can't, because the light's not reflecting off of something. And in order to see light, it has to reflect off of something. So what we do if we want to see the pattern formed by the interference of light when it diffracts through two openings is put a screen up here. This is our screen. On that screen, we're going to see not a bright line and a dark line and a bright line and a dark line, but rather just a spot on the screen that's bright. And then a spot right beside it on both sides that's dark. And then bright, and then dark, and then bright, and then dark, and so on. We get a series of bright lines and dark lines. Bright line, dark line. If we could see, yes we will actually, not today, but we will on the first of the week. If we could see the light interfering through here, then it would look exactly the same as the water waves would through there, with a bright line and a dark line and a bright line and a dark line and a bright line and so on. We just can't see it because the light's not reflecting off of something. Does that make sense? Now, we analyzed this interference pattern that we see on the screen using two equations that we learned yesterday. Lambda is equal to d sine theta over n, and lambda is equal to xd over n times L. There was one variable in each of these equations that we were pretty familiar with already, and that was lambda. Lambda was the wavelength of the light. There's nothing tricky about that. The wavelength of the light that goes through these two openings and produces this interference pattern. Okay, we've got red light drawn up here. That would be somewhere in the range of 7 times 10 to the negative 7 meters. Somewhere around 7.5 times 10 to the negative 7 meters. Okay, blue light would be somewhere in the range of, or violet light would be somewhere in the range of 4 times 10 to the negative 7 meters. Okay, the wavelength of the light is we know what light, we know what wavelength is. Okay, we're just talking specifically about the wavelength of whatever color of light that we're shining through there. The other variables, they're a little bit trickier. Let's take a look at the easiest one first. D. Who wants to tell me what D represents? Little d. Good. The distance between the openings. It's from the center of one opening to the center of another. Good. One of them's done. What about L, the next easiest one? Difference what? I'm sorry? Difference between the screen. You're close, not the difference between the screen. Katie?
The distance between the screen and the barrier.
Yeah. The distance between the screen and the barrier. And that's going to be measured in meters as well. X is the next one, but that's kind of a little bit tricky here. X is what? The distance between any maximum or minimum and any other maximum or minimum. So it can be the distance between, let's number these here before we start doing that. It can be the distance between the fifth maximum and the fourth maximum on the left-hand side. Or it can be the distance between the fourth maximum and the second minimum on the left-hand side. Or it can be the distance between the first maximum on one side and the fifth minimum on the other side. It doesn't matter. So how do we control for that? How do we get what we want to get out of one of these equations if we make x essentially whatever we want? We have to make sure that n is consistent with that. N is the difference in maximum number. So here the difference in the maximum number is from 4 to 5 is 1. Here it's from 4 to, what is this right here? The second order minimum we would say is not 1 or 2, but rather 1.5. So n would be, in this case, 2.5. 4 minus 1.5 is 2.5. What about this one? First one on the one side, the fifth order minimum on the other side. What's that number that we put there? 4.5. 4.5 minus 1, and would be equal to 5.5 there. Does that make sense? Dale, you had a question?
Does it have to go from minimum or maximum minimum? Like, or can it go minimum to minimum?
Yep, that's fine. Yeah, it could go min to min, max to max, or max to min, or min to max. Doesn't matter. Any minimum or maximum to any other minimum or maximum. Doesn't matter. Yep.
Does that like make the left side negative?
No, we're going to label them all as positives. But when we start subtracting things, if we're going across the central maximum, that 0 one, that central bright spot, then we're going to make one side negative when we're doing the subtraction. Doesn't matter which side. Okay? 4.5, sorry, would be 4.5 minus negative 1, or we would say 1 minus negative 4.5. Either way, you get 5.5. So we're still going to call them positive, but when you're doing the subtraction, make one of them negative. D is taken care of. N's taken care of now. The only thing we don't have taken care of is theta. Theta is an angle, obviously, but what angle is it? Well, it's an angle that's always measured from the central maximum to wherever we want. It can be measured to the third order maximum on the right side, or it can be measured to the second order minimum on the left side, or to the fourth order minimum on one side, or the 17th order maximum on one side, if you have 17 orders of maximum. Doesn't matter. It's not quite as flexible as x, because x can be from wherever to wherever. This one has to be measured from the central to wherever. Now, just like with x, we've got to be careful that we're consistent with n. In this case, n would be equal to what? Three minus 0 is what? 3. What would this be? From 0 to the second order min. N would be equal to 1.5 there. 1.5 minus 0 is 1.5. So now we've got all of these variables taken care of, including the tough ones, x, theta, and n. Did they make sense? I'm sorry? Theta is always measured from the central maximum. It's either to some maximum or minimum on this side, or it's to some maximum or minimum on this side. Doesn't matter. Well, you'd either be given it or you'd solve for it, one of the two. Yeah. just like all the other variables. Now there's two equations that you see down here. One of them has a star by it. Do you remember what I said about the star yesterday? Maybe it was another class that I mentioned that too. I mentioned in passing, just in passing, very briefly, didn't explain it, but I mentioned in passing to one of the classes yesterday that that star meant that this equation that you see right here, no, in fact, just the opposite. This equation is actually an approximation. It's not perfect. This one's perfect. This one is exact. This one is not exact. It's approximating it, and it works. It's a good approximation, a very good approximation, if the angle that we're dealing with is small. But how small? I'm not going to tell you. Why am I not going to tell you? Because it's going to mean extra work if I tell you. I'm going to give you a rule of thumb in a few minutes. Okay, a rule of thumb that will not require you to know what the angle needs to be in order to use that equation. The rule of thumb is much quicker, and it will always work for you. Okay, just keep in mind, as we're going through it, that this one is valid most of the time. It's a very good approximation, probably 95% of the time. But every once in a while, it just doesn't work for us. This equation is always valid. So if in doubt, what should you do? If in doubt, use this one. It just means sometimes a little bit more work, that's all. Okay, we got two example problems that I want to do today, and then that's it. 13.8 on page 689, first of all. This one says monochromatic light. Monochromatic, what does that mean? One, chromatic means color, so one color of light. When I drew the picture up here, I drew it for monochromatic light. Monochromatic red light. Okay, one very specific frequency. I'll show you the pattern that you would see in just a moment if you don't have monochromatic light. It looks a little bit trickier, it looks a little bit more complicated, but it doesn't actually change anything if you pay close attention to it. Let's finish this question, then I'll show you that picture of polychromatic light, more than one color. This monochromatic light is incident on two slits separated by 0.30 millimeters. We're going to circle that millimeters because we don't like that, and we're going to circle this whole 0.3, label it as D. That's the distance between the openings. The first bright fringe is located at 0.8080 degrees. That's going to be theta. The first bright fringe relative to the central antinode. Right? Here's my central. Here's my first bright fringe. N is going to be equal to 1. N is going to be equal to 1. They're telling us here. What's the wavelength of the light? Which one do you want to use? D sine theta over N or XD over N times L. Keeping in mind that XD over N times L isn't always valid. D sine theta over N, so it's not even an issue, right? We don't even have to check to see if anything's valid because this is by far the most convenient for me. D is 0.30 times 10 to the minus 3 times sine. Be really careful with the calculator on this one. I know that some of you guys are using radian mode in math class. You got to be in degree mode first of all. And I don't know about you guys, but for whatever reason, when I see an angle that's this size, that's 0.08, it's really small like that, I sometimes get tricked into using radians. I don't know why, but I do sometimes. Don't. Okay, in physics 30, you're always going to use degrees no matter what the angle is. Let's calculate that wavelength. What do we get? 4.2 times 10 to the minus 7. Now, I'm going to take a wild stab here and suggest that you're probably right. The reason I say that is because 99 times out of 100, literally 99% of the time, or better, you're going to get a 10 to the minus 7 answer here. Why? Because that's visible light. We're almost always going to be using visible light here. You're going to get a 10 to the minus 7. If you don't, it doesn't mean for sure that you're wrong. It just means you're probably wrong. It's worth checking at least. Okay? If you keep getting 10 to the minus 6, all right, go with it. But it's worth checking your work over. Make sense? All right, so what if this wasn't monochromatic light? What pattern do we see if it's not monochromatic, if it's polychromatic? Polychromatic means more than one color. Let's say it's all the colors of the rainbow. It's white light. Just like we shone white light on the prism. Remember it split up? Remember that was called dispersion? We had red, orange, yellow, green, blue, indigo, and violet. Now we're going to shine white light. We're going to shine white light on this. What happens then? Well, when white light is shone upon these two openings, we will get a series of bright spots and dark spots for each color. So it's going to look something like this. In the middle, you're going to see all the colors combined. It's not going to separate in the middle. You're going to see the white light. I'm making it yellow just because if I make it white, you're not going to see it there. Okay? You're going to see the white light in the middle. It's not going to split up. Nothing's going to happen to it there. It's just like that last diagram I drew you, right? Where the red light was a bright spot in the middle. But your next bright spot, let's say the next bright spot you see to the right will be blue. You're going to see another blue. You're going to see another blue, and so on and so on. And you're going to see that on the other side. But you're also going to see orange and yellow and green and indigo and red and so on. I'm not drawing all the colors here. I'm just drawing 3 of them. But there would be 7, right? Red, orange, yellow, green, blue, indigo, and violet. In other words, you see a bunch of bright spots, but you see a bright spot, you see more bright spots, right? Because you see a bright spot for each different color. Does that make sense? That doesn't need to change anything for us. It looks a little bit more confusing, but in the end, if you see a problem like this, you don't use the polychromatic light. You don't analyze the polychromatic light. You analyze red, or you analyze blue, or you analyze whatever color you're given data for. It splits up just like almost like it does with a prism, but you're not going to use all of the colors. You're going to pick one color that's convenient, probably the one that you're given data for. Now, in 18 years, I can probably count on one hand the number of problems that I've seen on an exam that have given you polychromatic light going through here. It's almost always monochromatic light, but I have seen it. What do you do if you see it? Pick a color and run with it. Make sense? Don't get messed up by seeing, they show you a picture of this, don't get messed up by that. Okay? Pick a color. Pretend the other colors aren't there. Okay? And treat it like you did the last problem. Now, I just want to take one quick note of a couple of differences between what you see right here with the diffraction grating and what you see here with the prism. What's one difference that you see? I mean, we see a rainbow up here, right? We see a bunch of rainbows down here, right? Not just one, but we see a bunch of them. What's it? Not a double rainbow, but a quadruple or quintuple rainbow or whatever it is. What else do you see that's different about it? I'm sorry? There's dark spots, yeah, in between the spectra. See, we have a spectrum here and a spectrum here, and in between the spectrum there's dark spots. We only have one spectrum here, right? So there's nothing to be in between. You see white light in the center, so in the middle you're not going to have that spectrum, right? It's just the white light. Which one refracts the least here? Red. Which one diffracts the least? Violet. Right? Red light bends the least. Violet light spreads out the least. Does that make sense? So your rainbow here is going to be red, orange, yellow, green, blue, indigo, and violet. Your spectrum here is going to be, as measured from the central maximum, as a frame of reference from the central maximum, our spectrum is going to be violet, indigo, blue, green, yellow, orange, and red. It's backwards. Does that make sense? Yeah, it's going to be Vibji Yob. Vibji Yob. Your. Give G your. Give G your. It's our, this is our Canadian guy that we used to remember the spectrum, and this is our Russian guy. Jib Gior. Does that make sense? Okay, guys, listen. It doesn't happen all that often that we have to know that. Okay, but it has happened. So we got to be familiar with it just in case. If you ever see it, again, don't sweat it because we know that we can just ignore all the other colors. You're going to be given data for, let's say, yellow. Go with yellow. If you're given data for red, then go with red, just like you did in this question. Okay? Just that when a lot of people see this, they're like, oh my goodness, what do I do? There's all these colors. What do I do with all these colors? Okay? Pick a color, erase the rest of them. Pretend they don't exist. Okay, we got one more example to do with you here. These are going to be homework on 689, practice problems that go with the example that we just did. But I want to get through this example before the bell goes, so I'm not going to give you a chance to work on those other ones quite yet. 691 says, a student measuring the wavelength of light emitted by krypton gas sample directs light through two slits that are separated by this distance. This is going to be D. I'm going to circle this because it's non-standard. This is going to be L. The distance between the second bright and the central bright spot is 2 minus 0 is 2. N is going to be equal to 2. Okay, they've already got that identified there. This is going to be X. But again, we want to identify that that's going to be, should be converted to meters. What's the wavelength there? What equation do you want to use this for this one? D sine theta over N or XD over N times L? Let's use lambda is equal to XD over N times L. Now, this equation is valid almost all of the time. This equation is valid in this situation. Here's the rule of thumb that you're going to use to determine when it is or when it isn't valid. If L is greater than 10 times X, let's take a look at L, 3 meters. What's X? 0.01 meters. Is L more than 10 times X? Way more than 10 times X. Is it valid? Yes. L was 0.0118, right? X, sorry, that was X. L was 3. Okay, it's way bigger than 10. Now, this rule of thumb that I've given you is conservative. It actually works a little bit outside this rule of thumb. You could get away with using this equation even if this rule of thumb doesn't say you can. There's the odd time when you could. But you know what? Let's just stick with the rule of thumb because it saves you a lot of work. Saves you a lot of work in actually calculating the angle to see if the equation is valid for you. So let's go with it. Even though it's not perfect, it'll never lead you wrong. It's just that every once in a while, you may have been able to use this when you decided because of this rule of thumb that you couldn't, that's all. Okay, let's do this here. X is going to be equal to 0.0118. D is going to be 0.264 times 10 to the minus 3. N is 2. L is 3.0 meters. What do we get there? Do you think we're probably right? We got a 10 to the minus 7, so yeah, we're probably right there. Is that good? Now, I got a quick question for you. You do have the questions that go along with that as for homework as well. Page 689 and 691. Quick question for you. If this equation wasn't valid here, which it is, right? But if it wasn't valid here, what would we do? How could we use the other equation, the only one that is valid, okay, if the second one isn't valid, when we don't know what theta is? Let's find it. If that's X, and this is L, then solve for theta. tan theta is equal to x over L. You can get theta, and then you can go back and use this equation. And you can do that every single time, but you don't have to do that every single time, because if we just use this little rule of thumb, we can sometimes, most of the time, recognize that this equation works for us. Good enough. Okay, make sense? So 689, 691 for homework this weekend. If you didn't finish the other stuff, let's get that done as well. And let's make sure your labs are finished for Monday morning as well. Monday afternoon as well. Okay? That's it.